Um, we just finished talking about um, evaporation and condensation, which usually happens at the surface of a liquid. If you're going from liquid to gas or at the gas liquid interface. But now let's talk about a more extreme example of evaporation. Under the right conditions, you can actually make evaporation happen beneath the surface of a liquid. So last time we talked about this is your liquid. Evaporation usually happens here at the top when you have molecules getting kicked out. But if we essentially really crank the heat up, we can actually cause evaporation to happen way under the surface. So we could actually get evaporation to happen down here. Um, and have these particles actually start leaving the liquid. And you've seen this anytime you've cooked anything like pasta where you're boiling the water. Um, when these particles start evaporating in the bottom of the pot, that's actually where you see the bubbles forming. That's the water becoming a vapor, and that vapor pushes out on the water, makes those bubbles, and then those bubbles are actually what get sent to the surface. So what you're seeing is the formation of those bubbles, and then you get sent upward through the water. Again, this change of phase occurs throughout the liquid and not just at the surface. That's because we're adding a whole lot of heat. Lots of energy. And the fact that we're adding a whole lot of heat, a whole lot of energy, that's what's causing this process of evaporation to happen everywhere. And of course, this is called boiling. And essentially, what's going on is the vapor pressure inside these bubbles. You can see here, we've got these force vectors pointing out. So let's see if I can zoom in. Perfect. The forces coming out are just from the vapor, but then that has to fight against the pressure of the water, which is pushing inward. So you've got the vapor pressure out, and then that has to fight against the water pressure coming in. And of course, the water pressure comes from the air pressure as well. So you've got the weight of the water, H2O, and you've also got the air pressure, the weight of the air above it too. And that's where that fighting pressure comes from. Normally, at 100 degrees Celsius or 212 degrees Fahrenheit, if you have just standard atmospheric pressure, around sea level and typical 100 degrees Celsius water, water molecules will have enough energy to exert a vapor pressure equal to the pressure of the surrounding water. And basically, all this means is that at 100 degrees Celsius and an everyday atmospheric pressure, water will boil in those conditions. So all the same as water will boil. Yeah, and we know that. That's no secret. But what's interesting is you can actually change the boiling point. So if we wanted to make the boiling point higher than 100 degrees Celsius, we could do that. Then your water would have to get so much hotter before those bubbles start forming. We could also drop it. We could drop the boiling point to like, I don't know, 50 degrees Celsius. And then all of a sudden, you have water that's boiling and it's not even that hot. Um, we can actually add extra pressure essentially by just adding more water on top of the water column. So if we make it harder for those bubbles to form, then the temperature of the water is going to get hotter. So this actually happens in a geyser, like Old Faithful in Yellowstone, or you can actually increase the air pressure on top, because we talked about that in the last slide. We have weight of the water plus the air on top. And if you increase one of those, then you can actually make water get hotter than 100 degrees Celsius before it starts boiling. So this does raise, essentially we're raising that pressure, raises the necessary energy. So those bubbles need to get more energy to fight against that extra pressure, whether it's coming from the air or the extra water. But essentially the boiling point is raised. So you can see here in the pressure cooker example, what's happening is we're getting an increase in pressure up here. So plus pressure. So if we have all this extra pressure up in the atmosphere inside the pressure cooker, that means we're going to raise the cooking temperature, or the temperature of the water. So maybe it gets to 105 degrees Celsius before it starts boiling. Maybe it gets to 125. I don't know. It just depends on the pressure inside the pressure cooker. But essentially, that's how you're going to cook things. You don't cook things just by boiling it. You cook things by getting the water hot. So if you really want to cook something, you need to increase your boiling point so you get your water so hot, and that will cook things faster and more thoroughly. In the case of like a geyser, you can see here that the water at the surface is only 93 degrees Celsius. So this is not boiling up here. But if you have all this pressure, so all this this water stacked up, just like if you dive to the bottom of a deep pool, you're adding a lot of pressure. So you can see that down here, the temperature is very hot. It's above 100 degrees Celsius, but boiling does not occur. So this is just very hot, but no boiling. So essentially your water can get superheated. Now what happens is once you get this narrow column of water and all of it heated up above 100 degrees Celsius, and by the way, all this heat comes from volcanic activity deep inside the earth, because these geysers can be really deep. So they actually get very well heated from inside the earth. So this raises the boiling point. You can get hot water that's like, as you can see here, 133 degrees Celsius. And eventually what happens is once it gets hot enough, the boiling will occur very rapidly at the bottom. And all those bubbles, they're going to come up very quick because they're very hot. And that's actually how you get geysers like this. And essentially, once this leaves, it cools down and starts the whole process over again. So this has got to stay there, get heated up well above 100 degrees Celsius. And then once the bubbles start forming, that's when the geyser goes off or explodes. Like evaporation, this is weird, but boiling is also a cooling process. I know that sounds weird, but it actually makes sense once you think about it a little bit. So at everyday atmospheric pressure, okay, so everyday life, we're going back to water boiling at its typical temperature of 100 degrees Celsius. We have no extra pressure, so this is what we'd expect. What's interesting though is when you start boiling water, like you could start with very cold water, start boiling it, and as soon as it gets to 100 degrees Celsius, its temperature actually remains constant. When it starts boiling, the water will not get any hotter. That's because it cools as fast as it warms. So this is important here. It cools as fast as it warms. Okay, so the amount of energy going in, right? Because we're adding energy, we're adding joules here. We're putting water or putting energy into the water, right? We're keeping it at 100 degrees Celsius, but because the water's evaporating, we're also losing energy up here. So as soon as water starts boiling, and it's important to note that this is boiling water, because you can keep heating up water from 5 degrees Celsius up to 100 degrees Celsius. But as soon as it gets to this point, it's going to stay at 100 degrees Celsius until it all turns to steam. And in typical fashion, we usually boil water by applying heat. But if we want to do something crazy, something else we can do is we can actually boil water by reducing the pressure that it's in. Okay. Now, remember, we just talked about increasing pressure makes it harder to boil. Okay, so increasing pressure is harder to boil water. But if we decrease the pressure, it's easier. That's kind of weird. And if you do it well enough, if you decrease the pressure enough, weird things start happening. So imagine if you were to place just regular old room temperature water in a vacuum chamber, and then you just suck out all the air inside of the chamber. It's a vacuum chamber, that's what you do. What actually happens is you start lowering the boiling point of water. Okay, so remove pressure will lower the boiling point. So the idea is essentially, if you think about a thermometer, water boils here, water freezes here at 0 degrees Celsius. What you're doing is you're moving this boiling point from here to somewhere down here, maybe, I don't know, 75 degrees Celsius. Because the more atmosphere you remove, the more you're going to drop this boiling point. So if you remove all the atmosphere, you can essentially move your boiling point down to where it's the same as the freezing point. And this is a very extreme case, but it can be done. So when enough atmosphere is removed, and that's hard to do, given this setup, even though this setup here looks like a small setup, sort of like a tabletop setup, it can still take a long time to actually remove enough atmosphere to make this happen. But if you can remove enough of it from the jar, the boiling point will actually be low enough to equal the freezing point. And that means you're going to have freezing and boiling at the same time. This specific point is actually called the triple point. And that's essentially where you can have all three phases of matter at the same time. So if you look over here at this GIF, which actually decided to work, what you're seeing ice floating in boiling water. And of course, since there's bubbles coming up, there's also going to be water vapor in there. So you actually have a solid because of the ice. You have a liquid because of the water. And you have a gas, all in there at the same time because of the water vapor. And this is the triple point. Basically, you have to suck all the air out of the atmosphere inside that container, and then the water will just start boiling and freezing at the same time. Let's sum this up with a really quick conceptual example. So the question is, when will water boil at a temperature lower than 100 degrees Celsius? And when will it boil at a temperature higher than 100 degrees Celsius. Okay, so how can we get away from that regular old boiling point of 100 degrees C? Well, like we've been talking about, water will boil at less than 100 degrees Celsius. So we're going to go less than normal. If the air pressure on its surface is reduced, so we're talking about reduced pressure here, and it will boil at higher than 100 degrees C. If we increase the pressure that it has to overcome for the boiling process to start. Okay, so we talked about boiling. Let's talk about melting and freezing. So sort of going the opposite direction. Instead of going liquid to a vapor, we're going to go liquid to a solid. But before we talk about a liquid to a solid, let's go solid to liquid. So as heat is absorbed, okay, so we're going to add heat to the object. Molecules vibrate more and more violently with less order, which makes sense because you have all those molecules in there making up the solid. If you keep adding heat in there, it's going to get warmer and the molecules are going to move more and more. If you can add enough heat to the solid, then those attractive forces between the molecules, they actually can't hold anymore. So that's like, you can imagine if you have solid butter and you start heating it up, adding heat, those molecules holding the butter together, they're going to start breaking down because they're moving so much. And then that's when your butter or whatever solid starts to melt. That's how you lose that nice shape and it starts just turning into goop. Obviously, freezing goes the other way. You start with a liquid goop and then you turn it into a solid. And substances, when they melt or freeze, that's always the same temperature. So they melt, freeze at the same temperature. So that means whether you're going from solid to liquid, or if you're going from liquid to solid, depending on the solid, I mean, for water, it's 0 degrees Celsius, but depending on what you're looking at, the point for these two transitions is going to be the same no matter which direction you're going. And of course, for water, that transition period in ordinary everyday life, no vacuums, is 0 degrees Celsius. When we think about freezing, let's go through this process and think about going the other way. So instead of adding heat, if energy is taken out of the system, like from a liquid, all those molecules are removing energy. The motion is going to slow down until the molecules are basically moving slow enough to actually stick together. So this is a withdrawal of energy from some sort of liquid, which means molecular motion diminishes. And then once that happens, all of these molecules will attract to one another. So cohesion, which would be those molecules sticking together, cohesion actually causes the molecules to vibrate around fixed positions. Basically, they have less freedom, right? So their positions, what they're going to do is fixed. And because they all become fixed like that, that essentially forms a solid. So obviously, this is the process of melting here. No, sorry, this is the process of freezing. Go. So a pure substance has a definite melting and freezing point, right? If it's something well known, we know exactly. And if it's something well known and pure, like pure gold, pure silver, we're going to know really close, like when this process is actually going to happen. So if someone gives you some sort of material and you want to test its purity, you could take a sample of it and melt it and see at what point it melts or freezes. because if you add any sort of like impurities, this will actually lower the temperature, because there's just sort of more junk in there that gets in the way of the melting and freezing process. Um, so that's one way. If you do like analytical chemistry, that's one method that you can use to identify unknown substances. Just like with adding impurities and changing your melting point or freezing point, um, you can add salt to water and actually decrease its freezing point. And I'm sure you all have seen at some point the like salt trucks driving on the roads and spreading salt. Um, this doesn't cause the ice to melt, um, and it doesn't. Uh, I guess that's the biggest misconception is people think that this causes ice to melt, and that's not the case. What adding salt to water does is it actually slows down the freezing process and actually makes it harder for water to freeze. So the whole idea is basically you're interfering with the structure that the water is trying to form. Because you'll remember that ice has a nice crystal structure type looking thing with all the molecules. This is ice. And then to get there, I mean, you just have water literally floating around. So you have all these water molecules moving around in all these different directions. The whole idea is they want to form this nice crystalline structure. What you can do is when you add these foreign ions, because water is a polar molecule, and you can add salt, which is an ion. And what happens is you just put more stuff in the way of these crystals trying to form. Uh, in addition to having more stuff in the way, you basically remove a lot of the water molecules that are on the surface. So the water molecules that are close to the ice that started to form, you can put more salt in the way there, and that sort of keeps them from freezing as much. So if you look here, normally what would happen, you would have pretty much just as many transitions back and forth. So you'll notice just with ice and regular water, you've got some transitions going this way, solid to liquid. But then at the same time, you've got some of the water jumping over to the solid side and filling in these gaps, these holes in the crystal structure. So notice as much going one way, it's the same as the other way. 3 red arrows to the right, 3 blue arrows to the left. But as soon as you add salt, what's going to happen is it makes it really easy for these molecules to leave the ice. So we still have 3 red arrows to the right, but because we have these ions and salt molecules floating around, notice how they're sort of in the way. They're on the interface of these 2 different phases of matter. So they literally sort of run interference and keep these water molecules from jumping over to the ice as well. So you'll see we only have one instance here of the actual liquid water trying to become ice. So in addition to running that interference on the interface, remember that if we think about a thermometer, and up here is 100 degrees Celsius where water boils, down here is 0 degrees Celsius where water freezes. Essentially what we're doing is we are taking this line and moving it down to like maybe -5 degrees Celsius. So we're making the point, we're making the water stay water a little bit longer, a little bit colder. That's the whole idea behind slinging salt out on the roads. And plus, it gives you some extra traction because the salt crystals are crunchy. Um, Something interesting here with these crystalline structures that we've been talking about, because of these structures in the solid phase, oops, as soon as you start applying pressure, like if you apply pressure to ice, the application of pressure will actually cause the ice to melt fairly quickly. And that's just because those ice crystals, you crush them, they're just crushed into a liquid phase. So it's essentially rapid melting. When the pressure is removed, so if you stop pushing on the ice, all that water that melted, it actually refreezes fairly quickly. Um, and this process is called, and it's hard for me to say this, I don't know why, it's a weird hangup I have, but this is regelation. And that's basically what you do, what process you make this ice go through every time you make a snowball. Because you basically take a clump of snow, you compress the snow with your hands, and that causes melting, right? That's how you can pack a snowball or pack snow, is the pressure causes it to melt. But as soon as you stop the compression, it refreezes. So you sort of get your snow back. It's just more compact. Okay. So we've talked about sort of these processes where we can go from a liquid to a gas through evaporation or boiling. We can go from a solid to a liquid through melting. We can go the other way through freezing. We can go from gas to a liquid through condensation. So here we're going to put all this together and talk about energy and changes of phase. So if we continually add heat to a solid or a liquid, it will eventually change phase. We know that. We've been talking about that. We heat up ice, we turn it into a liquid. We heat up the water, we can turn it into steam. But let's really think about this process and go through the whole transition from a solid to a gas. So yeah, here in words, we'll talk about that with this picture, but essentially a solid will liquefy and a liquid will vaporize. So the point here is the liquefaction and vaporization, basically some vocabulary. So for a substance to change its phase, you have to either add energy or take energy out. So when we started talking about going from a solid to a liquid, that's going to be adding heat. We can go the other way, but we have to extract heat. So you'll notice going from a solid up to a liquid, heat's absorbed by the substance, right? So we have to give it some energy to make that transition. Okay, and then again, if we want to go to a liquid, from a liquid to a gas, you have to give it energy to go in that direction. Now, if we want to go the opposite direction, if we wanted to go from gas to liquid, the object itself, we don't have to put energy in, we get energy out of it. The gas is going to give off energy to go back to a liquid. And then the liquid is going to give off energy to go back to a solid. So putting in energy goes through this cycle one way, removing energy, reverse it. All right, now let's actually talk about an example of going through these steps that you should be very familiar with. So an example would be a heat pump. And the particular example you've all dealt with before is the refrigerator. So a refrigerator is a type of heat pump. And what it does is it pumps heat from a cold environment to a warm one. I know that sounds weird, but if you think about it, what you're trying to do is you have some sort of barrier, and you've got cold food, cold groceries on one side. And what you're trying to do is you're trying to take any heat and pump it out. Okay, and that's the whole purpose of like all the crap that you've seen on the back of a refrigerator, all the coils and stuff, and then the compressor in the bottom. That's exactly what's happening. So let's walk through this refrigerator diagram over here. Essentially, a liquid is pumped into a cooling unit where it turns into a gas. Okay, now this is a special liquid, okay? So we need a liquid with a really low boiling point. So low boiling point. And that's really important. So I think a lot of refrigerators actually use Freon. So if we look over here at let's see. If we look over here at this example, I will switch this to blue for now. So what we're going to do is we're going to pump in the liquid. Mind you, it is not water. Okay, so this is a liquid going in. But now the boiling point is so low that the groceries inside, they're going to seem hot. So I'll just say the food inside it seems hot. So we have to pick some sort of coolant that will actually boil at a really low temperature, right? We want it to start going from a liquid to a gas. The only thing I can think of is Freon. If there's any chemists in the class, then they might have a whole list of things. But essentially, what we want to do is just take something that's with a boiling point so low that it'll actually suck energy from the inside of the refrigerator to start boiling. So it starts as a liquid, leaves as a gas, because it took that energy in. It took the energy in from the cold refrigerator, but because the boiling point is so low, it's going to boil anyways. Okay, so this is energy into the coolant that we're using and out of the refrigerator. Okay, now that gas, since it goes in as a liquid but comes out as a gas, the gas is then pumped into condenser coils. That's usually on the back of the refrigerator. Okay, oops. So that's going to go here. Now, this gas is going to start condensing. Okay, hence the name condenser coils. This is where condensation occurs. So you'll remember that as we go from a gas here, when it goes in originally, it's going to condense, and condensing means it's going to go from a gas to a liquid. So it leaves by the time it gets up here, it leaves as a liquid again. So essentially what happens is, since condensation is a warming process, you remember that from last time, since condensation is a warming process, you actually get heat out of the refrigerator. So it heats up the room. So that's really wild. Essentially what you're doing is you're taking some sort of coolant and you're sucking out as much of the heat inside the refrigerator, and then you move it over with a gas and then just dump all that heat out into the room. So a refrigerator will actually make your kitchen warmer, because the end result that you get out at the end of the day is the condensation from the condenser coils in the back. So obviously this is just a refrigerator. You can essentially reverse the process and get a heat pump that's going to like heat your home in the wintertime. let's look at this quick example. So is energy necessarily absorbed or released when a substance undergoes a phase change? Um, Keyword on necessarily. Does that mean, do we always have to have an energy exchange if we go from a solid to a liquid, or a liquid to a gas, or a gas to a liquid, or a liquid to a solid? And the answer is absolutely yes, always. And just as a reminder, the directions for adding or taking out heat or energy, it's right here. So adding energy will go one direction, removing energy will take you the other way. But there always has to be some sort of energy change when you're going to change phases of any substance. Oh, excellent. Okay, so let's do sort of one more example. Not really an example, but we're just going to take a 1 gram of ice with an initial temperature of -50 degrees Celsius, so it's pretty cold. And we're just going to essentially keep adding heat to it. Okay, we're just going to start -50 degrees Celsius and just dump in heat, and we'll just go through the whole solid to liquid to gas exchange. So the question is, how does the temperature and the phase of the ice change? Well, clearly, since it's at -50 degrees Celsius, it's going to start heating up. There's no phase changes in sight. We can totally take -50 degrees, add some heat, change it to -40 degrees, -30 degrees. But when a temperature of 0 degrees Celsius is reached, melting begins. Because remember, that temperature is actually our, for now, transition point for water. So this is water's transition point. Remember that the temperature of this ice water combination, because it's starting to go through a phase change, the temperature does not change at all. It stays 0 degrees until you get the full transition. So you got to go all the way from a solid, all of it's got to change to a liquid before you can actually get the temperature to raise again. So when this transition starts, you're hanging out at 0 degrees Celsius the whole time. Once that's done, once you finish going from a solid to a liquid, then you start heating the water up again. So now we can go from 0 degrees Celsius, we can heat that water until it reaches 100 degrees Celsius. Okay, this is another transition point for water, because this is its boiling point. It's getting ready to start boiling. So here's transition 2. And this is where the boiling begins. And that's where you go from a liquid to a vapor or a gas. So liquid to a gas. And again, this stuff is going to stay at 100 degrees Celsius until you get all of this transition. You have to get all the liquid changed to a gas before you can increase the temperature of the steam. So the steam can be 300 degrees Celsius. It doesn't have to stay at 100 degrees. It's just you can't have this transition at a different temperature. This whole transition has to happen at 100 degrees Celsius. Temperature does not change during the vaporization. And this, again, only the temperature increases only after all the water becomes steam. So that was this whole transition in words. Let's look at a plot. This will make this much easier. Right, so we started with a 1 gram of ice at -50 degrees. Well, we can heat that up, no problem. So you can see I have no problems going up from -50 degrees, adding heat. So that's what's going on here. I'm adding heat. until I get to 100 degrees. Now look at what happens. I keep putting heat in, but the temperature stays the same because melting is happening, right? During the transition, during this first transition, the temperature during melting stays at 0. Even though I'm still putting in heat, you can see my heat's increasing on the x-axis, but my temperature does not. The amount of energy required to change this right here, because I have to put in some amount of energy. So this is the latent heat of fusion. So I'm going to abbreviate this, the latent heat of fusion. Essentially what that means is I put in energy, Q, okay? But then when I get to this transition, I have to add more energy. Plus I have to give energy to go through to get through this phase transition. So I have to add the latent heat of fusion energy, right? And that's going to get me through this right here. So not only am I having to heat this thing up, I'm having to make sure I provide energy to get through the transition. Once I do that, so once all of my ice becomes water, I can start raising the temperature again. You can see that here. No problem. I can keep raising the temperature until I get to the other transition point, which is at 100 degrees Celsius. You can see for a really long time, I mean, look at how much energy I'm adding. I'm adding 2,260 joules, but even though I'm adding this much, the temperature is not changing. For this whole time here, the temperature is staying at 100 degrees Celsius. But that's because vaporization is happening. So I'm going from a water to steam, right? So this is a transition between the two. So this is transition number 2. Okay. And I still have to put in energy to make this transition happen. So this is going to be adding in the latent heat of vaporization energy. So instead of just heating the water, so I go from just heating water, now I go to have heating water plus adding in the extra energy for that phase change, the latent heat of vaporization. So that's the whole idea here is essentially you still have to, even when you get to a phase change, you still have to provide energy to get through that phase change and on to the next thing. And you'll notice, just like I said earlier, once you get through that phase change and all your water becomes steam, you can start increasing the temperature again. Because there's no upper limit on temperature. You can keep increasing that as much as you'd like. But that is essentially everything we needed to talk about for phase changes and the energy associated with phase changes. So we've covered evaporation, boiling, we've covered condensation, and freezing, and the condensing in the coils on a refrigerator. So that's pretty much all the phase changes that we need to cover. Here is the most formal we'll get about phase changes, just looking at the transitions on a plot. So the next thing we'll talk about is just the first and second laws of thermodynamics, and then we'll finish up heat transfer and thermodynamics for this course and move on to something else. So as always, if you have any questions, please send me an email and ask.